Hi guys, my name is Lauren Coleman. A little bit about me. I just finished my third calculus course at The Ohio State University and I have a passion for math. So before I move on to linear algebra, I wanted to share my knowledge of calculus with you. So in this video, I'm going to cover a basic overview of the topics you should know before going to calculus, which include functions, function composition, and trigonometry. So for those of you heading into calc for the first time, I'm going to cover these topics in the next 20 minutes to get you ready to rock and roll in calculus. So I split the video up into two segments. The first one will be the function and function composition review, and then later we're going to have the trig review. So to start off, just what is a function? So a function is some relation or expression so that every input has exactly one output. So one of the ways that I was first taught to visualize this is just imagine like a machine, and it plots to numbers. And so you put a number in, and then you just get a number out. It's just like the easiest. It's not always like linear like this, but one of the best visualizations is just thinking of it as a machine in your mind, that it plots one input to exactly one output. And so that kind of leads into the more formal names for input and output, which are domain and range. So domain is all the possible input values a function has. And then similarly, range is all the possible output values a function has. And so I just wanted to write them on the board so you can have a really clear, definition for what functions are, domain and range, and just other things that we're going to talk about. And so I just want to give a quick example. So I'm going to switch colors actually for this, so it kind of stands out a little bit more. So an example of an unrestricted domain would be something like a line. Let's say it's just a line y equals 3, or x plus 3. That was kind of bad. Just pretend it goes through it. So for this one, it's unrestricted because the domain can take any possible x value and the range can take any possible y value. And then this one is going to be an example of a restricted domain or range. And we're going to do just a basic parabola. And so this one is an example of a restricted range because the y values have to be greater than 0. And so it can't take any possible y value. Okie dokie. So now we're going to move on to just some ways that you can tell if a function is a function or not. So one of the ways you can tell if a function or relation / expression is an actual function is by the vertical line test. And so this, it's a good way to check if something is an actual function, because the way the vertical line test works is, let's say I have a cube root function or something. So what the vertical line test does is, if you draw a line through any point in the function, it should only hit the function once. And you can see in this function, it hits it, when the vertical line gets drawn, it hits it once. Perfect. It's a function. I'm going to draw like a counter example or a non-example. Let's say I had something like this. Well, if I draw a vertical line, it hits it 1, 2, 3 places. So that's definitely not a function. Okay, so if we say a function is invertible or and has an inverse function, what do we mean by that? Well, that basically just means that it means if you say a function is invertible, it just means that it has an inverse function. So think of the inverse function as undoing the function. So when we write f inverse, so I'm going to write f inverse, and then I'm going to write the mathematical notation for it, so when you see it, you won't be confused as to what it is. So you write f inverse is just f with, it looks like a little -1 up there. So basically what this does, so let's say we have our, oops, well, gotta map it differently actually. Okay, so let's say for just a regular function f, a lot of times you'll see f of x or capital F of x, and that's just saying that this particular expression is a function. So for f, we have the domain of f, I'll just write it like that, going to the range of f. Right? But for an inverse function, and this is the f kind of way, this is the way an inverse function works. So f inverse. That's this, the y actually ends up being the domain of f inverse, and the x actually becomes the range of f inverse. So what happens is, instead of mapping the x to the y, which you normally just associate, okay, x is equal to domain, y is range, but that's not always the case. With inverse functions, the y actually becomes the domain of f inverse, and then it maps to the x, which is the range of f inverse. So just something to keep in mind when you're working with inverse functions. And if I'm going a little bit fast, I'm just trying to get all of the information out, but I've definitely linked some resources that you can spend more time if you need more help or practice with any of these topics. Okay, so the next thing is the horizontal line test. So just like we have a test to see if the actual function is a function, we have a test to see if its inverse is a function as well. So let's say we have a something that looks like this, kind of a sideways parabola. So similar to the vertical line test, the horizontal line test works by, if you draw a horizontal line through a function, it should only touch the function in one place. So that works out here, here, here. Looks like this function's inverse would be a function as well. Let's see, a counter example would be like this. If you draw something like this, and you draw, okay, it works for up here, but as you get down here, it hits it in more than one spot, which means that its functions, the function inverse is not actually going to be a function, it's just going to be a relation. So the next topic we're going to cover is function composition. And so sometimes a function is plugged into another function as its input. And so that's what we call function composition. So its notation is like this. And so it kind of looks like fog. But basically it's just, the way you pronounce it is f of g of x, which just means that g of x is being plugged in for the input for f of x. Or let's say you wanted to write it g of f, so g of f of x. It's just the way you say it. So I actually have a couple examples for this one, because this one's a topic that pops up fairly often, and it's really important to get a good grasp on it. So let's say example 1. We have f of g of x for f of x equal to 5x and g of x equal to 4x plus 4. So this one is telling us we need to plug g of x in for the input of f of x. So f is going to be 5x, but instead of the x, we're going to put g of x. So 5 times 4x plus 4. So you distribute the 5, you get 20x plus 20. And so that would be how you would work through an example of function composition. Next we're going to cover function symmetry. So there are 4 types of symmetry. I'm going to illustrate them on the board. Okay, so first one is symmetry around the y-axis. So this is y-axis symmetry. And then in parentheses, I'm going to put even. Because y-axis symmetry is also known as the function is even or odd. It's just talking about its symmetry. And so, like you have even symmetry, you have odd symmetry. And so I'm going to draw like a rational function. So this is symmetry around the x-axis. And then you can have symmetry about the origin. Which kind of looks like a sine function or a cosine or some trig function. And then you can also have symmetry over a particular line. So let's say this is the line y equals x. It's kind of like the most common one that you're going to see, but you can see other types of lines that they just have symmetry around. So why do we care? So knowing if a function has symmetry or not, it reduces the amount of work we have to do later for like things like limits or anything like that. So if we know, for instance, if something has y-axis symmetry, if we're looking for holes or cusps or any discontinuities, we would only have to do the work on one side of the function because we know that the right side mirrors the left side exactly. And so if you are not lucky enough to have a graph, there's ways that you can test for function symmetry. So, actually, it's fine. So for y-axis symmetry, you're going to want to, instead of having, okay, so normally you have x comma y, as this is your ordered pair, so you're going to have, let's say it's like 5 comma 3. That's just plotting a point on the graph, right? So normally you have x comma y, that's like our base, no transformations or symmetry or whatever. And if you're looking for y-axis symmetry, make sure you plug the negative x in and then just leave the y the same. Because what this does, as you can see on this graph, if we have 5 on this side and we have negative 5 on this side, they're both going to have the same y value, so the y value doesn't change. And then for x-axis, you're going to do the same thing except switch the y. So the x is the same, but leave and plug a negative y in. And then if it has origin symmetry, it should have negative x and negative y. And then y equals x, or any sort of line that equals it, you should just plug in that, that value for your ordered pairs. So the steps for finding function symmetry without a graph are to substitute and then simplify. Okie dokie, so now we're going to cover, this is more of the function side of things, function families. And so there are all sorts of functions, and they're called families because they're just different groups and classes of functions. And because of transformations, the parent functions, or the ones that don't have anything done to them, are just called the parent functions, or like the base functions. So we have absolute value functions. And so these look like just kind of like a V shape. They have a kind of signature V shape, and the equation for that is y is equal. So my camera unfortunately ran out of space as I was talking about the absolute value functions, but continue. So the absolute value function is actually a piecewise function. So that means that absolute value of x, I'm going to write the definition, but I'm just going to finish writing out what the piecewise function is. Okay, so a piecewise function is a function that is defined by different functions on different parts of its domain. So what that means for the absolute value function is, for x less than 0, it's going to be negative x. For x greater than 0, it's just x. So as you move along the different parts of this domain, as you move along the x-axis, different x values, the function is actually built or made up of different functions that are pieced together, and that's why it's called the piecewise function. So that's the absolute value function. Now we're going to move on to constants. So this is another type of function you'll see fairly often, and they're pretty simple. They're not made up of really much. So let's say, and also, quick side note, get in the habit of labeling your axes. It just makes things a lot easier. Let's say you have x is equal to 3. So this is just going to be a vertical line. And then similarly, let's say you have y is equal to 5. That's just going to be a horizontal line. So those are pretty much just the constant functions. They can be, any number. They're just, what matters is just they're constant. So the next type of function is called the power functions. So these take the form of y equals x to the n. So let's say it's y is equal to x to the first, or just x. It's just going to be a linear, it's just going to be a linear function. Oh, and speaking of linear, equation for slope, because you'll need to know that, it's just y2 minus y1, x2 minus x1. So if you just have two ordered points, then you can definitely find the slope of a line. Okay, so let's say y is equal to x squared. It's going to be a parabola. Okay, let's say y is equal to x cubed. And then you can go y is equal to the fourth again. And I say again because these, it also just looks like a parabola. It doesn't look, much different than the y is equal to x squared. And it's because they, after you go past x cubed, the functions start kind of repeating shapes and they look similar. So that's a good thing to keep in mind. Okie dokie, so now we're going to just talk about polynomials for a quick second. They show up a lot. You just need to know how to deal with them. So polynomials are just sums of variables and exponents in an expression. Oops, and exponent. So that can pretty much just look like anything you can think of. So let's say it's 5x to the fourth plus 3y to the 9th plus, 12z squared plus ... Just anything that's connected by, addition, subtraction, things like that. So we only have a few functions left in our function review. So the next one is going to be our rational functions. So this is like a really basic one, like the most basic one. But this is the, oops, I didn't draw it. The graph of y is equal to 1 over x. So the reason there's kind of like a giant divide in their kind of like characteristic shape is because of things called asymptotes. And so asymptote is just like an invisible line that the function can't cross because of certain rules in math. And so for this one, there's going to be an asymptote over on the y-axis, which is just x equals to 0, because you can't divide things by 0. You can't do it. It just doesn't work like that. And so that's why there's an asymptote there. Okie dokie. So now we're going to move on to our second to last function, which are exponential functions. So these kind of just look like, like that. I got a nice swooping. So this is y is equal to b. I just picked b because that's what normally the base is called, and then raised to the x power. So one of the most famous exponential functions is y is equal to e to the x. And they all share the kind of same characteristic trait, but e, like pi, is one of those numbers that we use a lot, and they're irrational, which means they don't really have an end. Just y is equal to e to the negative x. So instead of looking like an upward swoop like this, it kind of goes in a downward swoop like that. And so exponential functions also have an inverse. They're invertible. And so logarithmic functions are the inverse of exponential functions. Which is kind of neat. Okie dokie. So it's going to be like an invisible kind of line there. This function is y is equal to e to the x. And then this function that I'm going to draw in blue is going to be the logarithmic function. So it's not the best drawing, but that's just basically what they look like, and they're mirrored over each other like that over the line y equals x because they're inverse functions. So the equation for logarithmic functions are y is equal to log base b of x. And then a famous example for a logarithmic function would be just natural log of x. So y is equal to natural log of x. And so this is the inverse of y is equal to e to the x. Oops, I didn't draw it yet. Yeah. And so last thing I'm going to do is write the rule. Okay, so this last part of the function and function review section, or function and function composition section, is going to be review of exponential and logarithmic rules. And before I showed you how the exponential function and logarithmic function were inverses of each other, which means just, that they undo each other and whatnot. So what you're going to see as I go through these rules, I've already written them in the interest of time, but a lot of the rules are going to look really similar and feel kind of similar, especially with the mechanics as you work through problems with that, and that's just because they're inverses of each other. Okay, so let's say you have log base, or a to the n times a to the m. Oops. If they have the same base, what you can do is actually add the exponents, which is really helpful. And then similarly, if you have a to the n divided by a to the m, you can subtract the exponents. So let's say you have b to the negative n. So anything to the negative exponent, it just gets put under a fraction. So 1 over b to the n, or whatever that exponent was. And then anything to the 0 power is just going to be equal to 1. That's extremely helpful if you have a long string of numbers and expressions, and you just see at the end it's all raised to the 0 power, then it's just 1. Let's say you have you have a b to the n to the mth root. It's just going to be b to the n over the m. And so what I like to do if I have like kind of a complicated expression and I'm not really sure which way it goes, I always remember the let's just say it's x, y, like this, and let's say it's all to the third or something like that, and I'm not sure which way to write it. always remember that if it doesn't have an index in here, which is what this little number right here is called, if it doesn't have an index, it's implied that it's just index 2, which is just a square root. And so if it was just, let's just say it was just x times y, you can always rewrite square roots as something to the 1/2 power. And so it's helpful that if it's just, another exponent in there that's not 1, you can just replace the 1 and the 1/2 with whatever number that is, which is actually pretty helpful. And then the last one for the exponential rules is anything raised to the first power is just itself. Okay, so these are the logarithmic rules. So log base b of xy is just equal to log base b of x plus log base b of y. And so it's really nice in both of these instances, if it has the same base, then you can do a lot more if it has different bases. And you can actually, if it does have the same base, or you want it to have the same base, you can use the change of base formula, which I will link below. Okay, so log base b of x divided by y, it's the same thing as kind of the exponential. You can just subtract the x and the y. And then log base b of x to the r, you can bring the exponent down in front, which is really helpful, especially with logarithmic differentiation, which we'll cover later. It's really helpful to be able to just kind of break apart, big, heavy expressions like that. And then log base b of x, if it's equal to log base b of y, then x is just equal to y. So here's our last section, the trig review. So I'm going to first start off with doing, the most basic kind of trig thing there is, the right triangle. So it's an example of a right triangle. And I'm just going to label the sides A, B, and C. And then I'm going to call this angle theta. So trig functions are what you may also know as circular functions. And so the kind of really good mnemonic device that you will see a lot in trig classes is the acronym SOHCAHTOA, which stands for sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And so what these side labels are, or what this acronym corresponds to on the right triangle, is in relation to the angle theta, how are these ratios playing out? So sine, for instance, is going to be opposite over hypotenuse. So this is theta. The opposite side of theta is b, and then the hypotenuse is c. And then similarly, cosine is going to be adjacent over hypotenuse. And so in this case, it's going to be a over c. And then tangent is going to be opposite over adjacent, which means that in this case, it's going to be b over a. So that's just a quick example of how, a right triangle works and a breakdown of the acronym SOHCAHTOA. So another thing that's really helped me out when I've been doing my trig is this thing called the trig rainbow. So it's basically a really handy way of being able to visualize how these different trig things are related. So we have the three basic sine, cosine, and tangent trig identities, or not trig identities, but trig functions. But then we also have cotangent, secant, and cosecant. Sorry. So what the trig rainbow is doing is it's giving you a way to remember what each of these stands for. And so it's basing it off of the three basic ones. So for instance, all of the cotangent, secant, and cosecant are reciprocals, which means it's just like a flip of these sine, cosine, and tangent. So for instance, tangent is normally sine over cosine, but cotangent is cosine over sine. And you can remember that as it just being 1 over tangent. And so if you remember how kind of fractions work, let's say you have 1 over tangent, and tangent is actually equal to sine over cosine. It'll just give you a way to quickly allow you to do, this division, and it ends up being cosine over sine. And so that's what it does for all of these, actually. And so secant is 1 over cosine, and then sine is 1, or cosecant is 1 over sine. And so that was one of the most helpful tricks I've learned in Trig. And it's just a really nice way to visualize everything. And so the other kind of basic thing that you learn in Trig is called the unit circle. And so it's based off of a circle with a triangle in it, and it goes out 1 unit. So this would be, the hypotenuse would be 1. And so let's say we have theta right here, and this will be cosine, and then this right here, this side will be sine. Yeah, so this is basically what the unit circle talks about, and what we use it for is all of these really helpful angle measures in radians, which is basically just another way for angles to be, denoted. Because most of the time they're called with degrees, but there's another thing called radians, which you use in the unit circle, and that is how it's just another way that you can name angles. So I'm just going to write down all of these angle measures in radians, and then I'm going to kind of quickly show you a conversion factor. Okay, so you'll notice that I only wrote down the first quadrant. I'm going to link below in the description a full kind of picture of it, but I think it's really helpful if you just memorize the first quadrant, which is what I did. You memorize the first quadrant, and then you can count around the unit circle. So if you count in terms of pi over 6s or 30 degrees, it'll make your life a lot easier versus having to memorize the whole thing if you're short on time or anything. So let's say I'm going to count in radians first, and then I'll tell you what the degrees measure. So pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. Okay, so basically what I just did was counted around the unit circle in degrees of 30. So I said 30, 60, 90, 120, 150, 180, 210, etc., all the way to 360 degrees. And so I'm going to tell you the radians to degrees conversion, just so you will know it, and it's not so daunting. Okay, so let's say you start off with a radian measure. So this is the radian to degrees. So let's say you start off with a radian measure. You're going to multiply that radian measure times 180 degrees over pi, and that will get you your equivalent degree measure. And then similarly, let's say you start off with degrees this time, and you want to go back to radians. Radians. You're going to multiply that degree measure by pi over 180 degrees. So I'm going to show you just a quick example, just to show you that it actually works. So let's say we are given pi over 2, and we want to convert that into degrees. So we're given the radian measure, so we're going to use this first one. So it's pi over 2 times 180 degrees over pi. So, let me rewrite this actually. The pi's are going to cancel. Then we have 180 degrees divided by 2, which is 90 degrees, which is, we know that to be true. So we can also do it, let's say for, let's say we're given 30 degrees and we want to convert it and actually see if it equals pi over 6. So we have 30 degrees times pi over 180 degrees. So the degrees cancel, and then we're just left with 30 pi over 180, and then we can, of course, simplify that to be 3 pi over, so pi over 6. So this is just a quick, overview of the unit circle, radians and degrees, the trig functions, things like that. So you'll get a good, basis of understanding for all of those things. And of course, I will link more practice resources if you are struggling in that area or just need a little bit more support, so you can get a full, more in-depth picture of that. Okay, so the last thing I'm going to do is take a review of the Pythagorean identities. So I'm just going to redraw this really fast. But you remember the unit circle and how I said this was cosine, this is 1. Should probably draw it a little bit bigger. Okay, so this is unit circle, this is theta, this is cosine, this is sine, this is 1. You remember the right triangle I drew above before? I think it was A, B, C, and this was theta. You might have heard of the Pythagorean identity a squared plus b squared equals c squared. Well, that's exactly where this first identity is going to come from. So it's going to be sine squared x plus cosine squared x equals 1. And that's just the basic Pythagorean identity that comes just from the a squared plus b squared equals c squared. Okay, so from this first basic identity, I'm just going to write down the other two Pythagorean identities, and then I'll tell you exactly where they come from. Okay, so from this first identity, you can basically just divide by sine squared x or cosine squared x and get these resulting two. So let's say you decide to divide by sine squared x. So you would have 1 plus cotangent squared x is equal to cosecant squared x. So that's where you get the second one. And then similarly, if you decided to divide by sine, you would say, okay, so this is tangent squared x plus cosine divided by cosine is 1, and then 1 over cosine is just secant. So that's all for the video today. If you have any questions, be sure to leave them down in the comments below and I'll answer them. Also, I've linked some helpful practice resources in the description box below. Thanks for watching.